The future is arriving faster than most people realize, and artificial intelligence to solve pervasive Internet of Things issues helps you get ready for it. We will focus on what it says about data and communication. Stay with me, the best part is near the end. Chapter 1: Impact of Artificial Intelligence on Future Green Communication. Introduction: The history of artificial intelligence, a roadmap of using artificial intelligence for green communication. Key technologies to make 5G in reality using artificial intelligence. Features of artificial intelligence-based green communication. Conclusion. Acknowledgement. References. Chapter 2: Knowledge Representation and Reasoning in AI-based Solutions and IoT. Introduction. Background. Knowledge representation and reasoning. Knowledge inference, forward and backward chaining, and KL1 languages. Artificial intelligence for information technology operations. AI, KRR, and IoT functions. Artificial intelligence applications and tools. Machine learning and deep learning. Robotic process automation. Internet of Things. Natural language understanding and interpretation. Learning using privileged information. Picture archiving and communication. System infrastructure-based mobile networks. Dynamically created mobile ad hoc networks. Intelligent agents. Conversational and natural intelligence. Advanced metering infrastructure. Distributed automation networks. Optical character recognition and human mind. Simple neural and biological neural networks. Machine intelligence. Learning and deep learning. Upper ontology and machine translation. Frame problem and CYCL projects and semantic web of things. Presenting, reasoning, and problem solving. Simple neural networks, artificial neural networks, and natural language processing. Contextual artificial intelligence perspectives. Complex artificial intelligence systems and swarm intelligence. The impact of smart dust on IoT technology. The next generation of computers and functional trends. Conclusion and future reading. References. Further reading. Chapter 3: Artificial Intelligence, Internet of Things, and Communication Networks. Introduction. Machine learning, artificial intelligence-assisted networking. Artificial intelligence in communication networks. Transforming optical industries by artificial intelligence. Artificial intelligence in optical transmission. Artificial intelligence in optical networking. Advantages of machine learning in networking. Optical technologies to support Internet of Things. Applications of Internet of Things with optical technologies. Conclusion. References. Chapter 4: Internet of Intelligent Things, Injection of Intelligence into IoT. Introduction. Methodology. Architecture of Internet of Things. Security and privacy. Artificial intelligence and Internet of Things. Applications of Internet of Things. Conclusion and future directions. References. Chapter 5: Artificial Intelligence and Machine Learning Applications in Cloud Computing. Introduction. Application of machine learning in different sectors of society. Artificial intelligence with multiple application fields. Application of Internet of Things in medical field. Conclusion. References. Further reading. Chapter 6: Knowledge Representation for Causal Calculi on Internet of Things. Introduction. Background. Knowledge representation. Dynamic knowledge representation. Intersection of knowledge representation, causal calculus, and Internet of Things. First-order logic and predicate calculus for KR, CC, and IoT. Structural causal model. Perl S2 calculus. Perl S2 operator. Perl S Bayesian networks. Halpern. Perl causality. Schaefer S probability trees. CP logic from Prolog and Problog. Probabilities and causal relationships. Mathematical rules for do calculus. Bayesian networks. Simulation and equivalence class. Future research direction. Conclusion. References. Further reading. Chapter 7: Examining the Internet of Things based elegant cultivation technique. Introduction. Internet of Things issues to consider before designing your elegant farming solution. Applications of Internet of Things in agriculture. Why will Internet of Things? Future of Internet of Things in agriculture, smart or elegant farming. Conclusion. References. Chapter 8: Machine Learning and Internet of Things for Smart Processing. Introduction, Information Labeling and Information Segmentation, Machine Learning Tools, Computer Vision and Neural Network, Challenges and Solutions, Research Questions, Examination and Results, Web and Image Mining for Medical Diagnosis, Conclusion, References. Chapter 9, Intelligent Smart Home Energy Efficiency Model Using Artificial Intelligence. Introduction, Literature Review, Energy Efficiency Model, Need for Energy Efficient Intelligent Smart Home Model, Basic Terminology used, Components of Proposed Model, Working of Proposed Model, Technology used in making the proposed model, Comparison between models, Advantages of Proposed Model, Applications of Proposed Model, Conclusion and Future Scope, References. Chapter 10, Artificial Intelligence-Powered Healthcare Internet of Things Devices. Introduction, Role of Internet of Things in Healthcare, Ease of Treatment, Uses for Healthcare Establishments, Encountering Possible Challenges and Vulnerabilities, Innovation and Business Perspective of Internet of Medical Things, Robotics and Nanotechnology, Amalgamation, The Implication of Nanotechnology Complementing Government Schemes, Conclusion, Reference. Chapter 11, Intelligent Energy-Oriented Home. Introduction, Smart Homes, Ambient Intelligence, and Smart Grids, Architecture for an Intelligent Energy-Oriented Home, Implementation of Systems for Illustration of Intelligent Behaviors in an Intelligent Energy-Oriented Home, Test and Analysis of the Intelligent Energy-Oriented Home, Conclusions and Further Developments, Acknowledgements, References, Further Reading. Chapter 12, Corporate Cybersecurity Strategy to Enable Artificial Intelligence and Internet. Introduction, Cybersecurity, Understanding the Cyber-Adversarial System, Threat Vectors, Internal and External Threats, Non-Malicious Non-Compliance, Malicious Non-Compliance, Financially Motivated Cyber Attackers, Ideologically and Politically Motivated Cyber Attackers, Anatomy of a Cyber Attack, Why Cybersecurity and Why Corporate Strategy, Cybersecurity Laws, Causes of Cybersecurity, Inertia, 3Is of Corporate Cybersecurity Strategy, Cybersecurity Systems Engineering, Enterprise Architecture Frameworks. Zachman Framework, U.S. Department of Defense Architecture Framework, Service-Oriented Architecture, Cybersecurity IT Portfolio Management, Smarter Cybersecurity, Leveraging Artificial Intelligence, IoT and Growing Cybersecurity Risk, The Change Management Challenge, Cybersecurity Expertise, Assess Current State, Making Cyber Part of Corporate Strategy, References. Chapter 13, Role of Artificial Intelligence and the Internet of Things. Introduction, Artificial Intelligence in Agriculture, Components of Artificial Intelligence required in agriculture, Role of Machine Learning in Agriculture, Models for Farmers, Services, Internet of Things Applications in Agriculture, Currently Used Artificial Intelligence and Internet of Things Technologies in Agriculture, Challenges with Artificial Intelligence and Internet of Things in Agriculture, Conclusion, References. Chapter 14, Integrating Artificial Intelligence, Internet of Things Technologies to Support. Introduction, Medical Devices and Healthcare Systems, Problems in Conventional Medical Systems, Categories of Medical Devices, Internet of Things, Artificial Intelligence in Medical Devices and Healthcare, Enabling Technologies of Internet of Things in Medical Devices and Systems, Monitoring using Internet of Things, Artificial Intelligence in Medical Devices and System, Critical Issues and Challenges of Internet of Things in Medical Devices and Systems, IoT, Medical Devices and System Security. Scalability, Conclusion, References. Chapter 15, Impact of Artificial Intelligence to Solve Pervasive Issues. Introduction, Sensor Network Technology, Pervasive Issues related to sensor networks, Role of Artificial Intelligence to solve pervasive issues of sensor network, Features of Artificial Intelligence in the Internet of Things Revolution, Conclusion, Acknowledgement, References. Chapter 16, Communication and Wireless. Impact of Artificial Intelligence on Future Green Communication, Akanksha Shrivastava 1, Mani Shekhar Gupta 1, 2, and Gajit Kaur 1, 11 Department of Electronics and Communication Engineering, Delhi Technological University, Delhi, India, 22 Department of Electronics and Communication Engineering, National Institute of Technology, Hamapur, India Information and Communication Technology is exploring artificial intelligence, AI, with a goal to lead it in advanced communication system networks to offer new features and services, and to enhance the quality of experience and network efficiency. The AI technology manufactures machine slaves to perform several complex tasks and activities in laboratories and industries. As mobile subscribers are increasing, the number of base stations, BSs, will also increase. Minimizing the power consumption of BSs and enhancing the energy efficiency are crucial issue of present era. This energy-efficient communication is referred as green communication. This chapter presents the impact of AI to make communication system green. Started with brief history and foundation of the AI technology, followed with the roadmap of AI for green communication. In next phase, several key technologies, applications, practices of AI, and future research perspectives are covered for new researchers working in this emerging research area. Artificial intelligence, green communication, MIMO, massive MIMO, millimeter wave, device-to-device communication introduction. Future wireless communication networks, 5G, will be highly complex and composite networks due to the integration of the different wireless and wired networks. This integration is known as heterogeneous networks, HET nets, where each network is having its different protocols and properties. 1. This combined HET net is having various critical challenges for network scheduling, operation, troubleshooting, and managing. In the ongoing scenario, the technology paradigm shifts from user-centric to device-oriented communication, which is responsible for converting the simple wireless networks into a complex form. Nowadays, to justify and resolve the operational complexity of future wireless communication networks, several novel approaches like cognitive radio, fog computing, Internet of Things, IoT, and so on have become very important. The artificial intelligence, AI, is one of the most promising approaches to make the adoption of the new principles, which include learning, cognitive, and decision-making processes, for designing a strongly integrated network. Integration of AI with data analytics, machine learning, and natural language processing approach is used to improve the efficiency of the future wireless network generations. There are remarkable growth and progress in AI technology, which facilitates to overcome the problem of human resource deficiencies in many fields. Among the countries, the competition of becoming a global leader in the field of AI has officially started. Most of the countries like India, France, China, Japan, Denmark, Canada, Finland, Italy, Mexico, the United Kingdom, Singapore, South Korea, North Korea, Taiwan, and the UAE, have already represented their strategies to endorse the development and usage of AI policies, too. These countries are promoting the various tactics of the AI techniques like technical research, AI-based products, talent, and skills development, adoption of AI in private and public sector, standards and regulations, and digital infrastructure. Is representing the top 10 countries' rankings in AI Index in the year of 2018-19. Top 10 countries' rankings in Artificial Intelligence Index with score in the year of 2018-19, 3. Country ranking score: Singapore 1, United Kingdom 2, Germany 3, United States of America 4, Finland 5, Sweden 6, Canada 6, France 8, Denmark 9, Japan 10. The history of artificial intelligence (AI) is one of the latest topics for research in advanced wireless communication system. A very interesting fact related to this technology is that this is much older technology than you would imagine. The concept of intelligent robots was presented by Greek myths of Hephaestus' mechanical men and Taylor's bronze man. 4. Some important milestones of the journey of AI from an initial state to till date are represented pictorially as in History of AI. AI, artificial intelligence. The foundation of artificial intelligence. Artificial neurons. The artificial neurons were the first model of AI, which was proposed by Walter Pitts and Warren McCulloch in 1943. Hebbian learning, a modified rule of construction of neurons, is presented by Donald Hebb in 1949. This rule is known as Hebbian learning. Turing test. This test can evaluate the intelligent behavior of a machine and also compare it with human intelligence. An English mathematician, Alan Turing, author of Computing Machinery and Intelligence, has proposed this test in 1950. Logic theorist. The first AI-based program that was organized by the Herbert A. Simon and Alan Newell in 1955. Dartmouth Conference. The AI technology was the first time adopted by the American scientist John McCarthy in the academic field at this conference in 1956. Progression of artificial intelligence. After the year 1956, the researchers have invented high-level computer languages like COBOL, Pascal, Lisp, and Fortran. These language inventions increased the scope of AI in society. 5. ELIZA, the first AI-based algorithm developed by Joseph Weizenbaum, is known as ELIZA in 1966. This algorithm is used to solve the problems of mathematics. Wobot 1. Japan has constructed the first humanoid intelligent robot known as Wobot 1 in 1972. First AI winter. This is the time duration, from 1975 to 1979, when the interest of AI was reduced due to the scarcity of funding for the research of AI. Expansion of artificial intelligence and expert system. After the first AI winter period, AI came back again into the light as an expert system in 1980. This system has ability to take decision like human expert. In this year, the first national conference on AI was organized at Stanford University. Second AI winter. The time duration from year 1987 to 1993 was the time duration of second AI winter. AI in home and business. At the year 2001, first time AI-based application, a vacuum cleaner used in the home. After that, AI entered into business world. Companies such as Gmail, Facebook, Instagram, Twitter, and so on. Modern artificial intelligence. Now AI is the most significant technology, which is used in almost all areas. The concept of machine learning, deep learning, cloud computing, and big data are just like a boom for the present scenario. Many well-known leader corporate companies like IBM, Google, Flipkart, and Amazon are focusing on AI for making their remarkable devices to provide their users with a better quality of experience. The future AI technology will be based on a high level of intelligence and amazing capacity and speed. 6. Machine learning. Machine learning concept is one of the types of data mining techniques. Machine learning is an approach of analyzing data, absorb from that data, and then make a decision. Now, most of the big companies use machine learning for their working operations, like YouTube uses machine learning to offer better suggestions to their subscribers of the movie, shows, and videos that they would like to watch. Deep learning. Deep learning is a subclass of machine learning. It is functioning like machine learning, but it has some distinct capabilities. The key difference between machine learning and deep learning is, machine learning model requires some guidance to take accurate decision, while the deep learning model does it by itself. The good example of deep learning is automatic car driving system. Roadmap of using artificial intelligence for green communication. This will be a great step to introduce AI technologies in the field of wireless communication systems. Incorporation of AI technologies in the field of signal processing and pattern recognition has represented the amazing results. 7. Presently, the key concern of the AI technologies in wireless communication systems is to find out the accurate wireless node position, proper resources allocation and optimization, and secure data transmission without delay. However, new research is to think about how to incorporate AI schemes into wireless communication. Compared to the conventional wireless communication systems, the new AI-based wireless communication systems should have four eminent aptitudes. These aptitudes are analyzing aptitude, thinking aptitude, learning aptitude, and proactive aptitude. The new framework of AI wireless communication systems with these aptitudes is illustrated in Framework of AI wireless communication systems with aptitudes. AI, artificial intelligence. Architecture of artificial intelligence-based green communication. The future wireless communication networks should have inherent capabilities like low latency, ultra-reliable communication, and intelligently manage the resources, energy efficient, and combination of IoT devices in a real-time dynamic environment. Such communication necessities and core mobile edge requirements can only be accomplished by integrating the fundamentals and principles of AI and machine across the wireless infrastructure. Represents the wireless network architecture with AI principles for a different environment. The integration of various latest communication technologies used for greening communication in different scenarios, urban, suburban, and rural areas. Energy-efficient wireless network with AI principles analyzing, cognitive, and decision-making. AI, artificial intelligence, millimeter. Optimization of network using artificial intelligence. Effective data gathering and information acquisition are the most essential requirements for optimizing the future wireless communication system. To extract the relevant information from the collected data in an effective manner is under the processing of data. In the third step, researchers analyze this received information and apply various aptitudes on it. Finally, at the last step, an optimized decision is presented which converts the wireless network into an optimized network. Represents the network's optimization process to identify best network for better CoE. Network optimization by artificial intelligence technique. Key technologies to make 5G in reality using artificial intelligence. The necessity to deal with this rapid progression of wireless services has required a large research activity that explores what are the optimal options for designing of user-oriented, context-aware next-generation 5G wireless communication network. The key components for 5G are multiple input, multiple output, MIMO, massive MIMO, ultra-dense deployment of small cells, millimeter, wave communications, and device-to-device, D2D, communications have been recognized. The integration of these technologies in the wireless system with the cooperation of AI principles in the most effective manner is a challenging task for operators and researchers. Multiple input, multiple output. This is the most promising approach to consider the development of the next-generation wireless network system. In this technique, multiple antennas are situated at both the end transmitter, source, and receiver, destination, 9. For enhancing efficiency and reducing the errors of the network, these antennas are associated effectively, 10. This technique facilitates to multiply the capacity of the antenna more than 10 times, without increasing the power and bandwidth of the system, 11. This CoE-focused approach has made it an essential element of the wireless communication network, 12. The comparison of MIMO with single input, single output, multiple input, single output, and single input, multiple output is given in Comparison of multiple input, multiple output, MIMO, with single input, single output, CISO, multiple input, single output, MISO, and single input, multiple output, CMO. No. Chapter 17, MIMO. Simple circuitry known as receive diversity known as transmitter diversity improve channel capacity 2. Diversity not required easy to implement reduce the problem of interference improve channel throughput 3. Low throughput high cost than CISO high cost than CISO highest cost 4. Channel bandwidth is limited. Problem of battery drain. Channel capacity is not improved. Complex circuitry. Massive MIMO. This technique is not only energy efficient but also spectrum efficient. Massive MIMO, MMIMO, is one of the advanced versions of technologies of MIMO, having several antennas at the base station of the communication system. This technique requires shorter wavelengths, higher frequencies, because the system needs to physically pack more antennas into a small area than the other mobile networks, 13-14. The main advantage is that a base station can serve multiple subscribers simultaneously within the same spectrum. Represents the architecture of the massive MIMO technique, where 10 to hundreds of antennas are serving for the communication process simultaneously. Massive multiple input multiple output technique in 5G network. Ultradense network. In the new age, ultradense network, UDN, has emerged as a prominent solution to fulfilling the requirement of enormously high capacity and data rate of the 5G wireless network. Qualitatively, this network has a much higher density of radio resources than that of other existing networks in the telecommunication market, 15-16. In literature, there are various definitions of UDN suggested by various authors. In reference 17, the author has defined the UDN as a network where the access point and base station density exceeds the user density in a particular area. In refs 18-19, a UDN is considered as a network where the distance between the access points and base stations is only a few meters. The architecture of a UDN is showing in. UDN plays a vital role in converting the communication into green communication. In this technique, the access points and base stations are presented very close distance to the mobile subscribers. The relation between the power and distance shows that the distance is directly proportional to the power. So, if the distance between the mobile subscriber and access point will reduce, the power of the communication system will automatically reduce. In this way, by minimizing the power consumption, a UDN promotes energy-efficient communication. Architecture of ultradense network. Millimeter wave. The waves are one of the most important approaches for the next generation of wireless networks. For delivering fast multimedia services, high-quality audio, video, and real-time services, a large amount of bandwidth is required. To solve this problem of spectrum scarcity, wavelength will be used in 5G network communication system. The signals are operating between the range of 30 and 300 GHz and being shifted to a higher spectrum. A large amount of bandwidth is offered at wave frequencies as compared to the bandwidth used by 4G and earlier wireless generation networks. Device-to-device communication. D2D communication is one of the effective technical approaches to reduce the consumption of power and improve the data transmission rate. 20. In this technique, two physically separated nearby located cellular nodes can directly communicate with each other with low transmit power and high spectrum utilization efficiency without considering the base station in the communication process showing in. The D2D communication approach is recognized as a public safety network for future wireless communication by Federal Communications Commission because of the low cost and high data rates offered by this technique. Architecture of device-to-device communication. Features of artificial intelligence-based green communication. The present era is based on perceptual, cognitive, and computational intelligence. So, telecom researchers and operators are on the path of creation of AI-based green communication system. For the adoption of AI technology, government and other agencies are encouraging the development of AI algorithms and investing funds and resources for AI-based research activities. By these full supports, the operators have achieved success in the sequence of effective practices in several fields and accomplished productive results. Application and practices of artificial intelligence-based green communication. Nowadays there are various applications of AI, from collecting data to give an optimized output. The aim is to apply AI in the mobile industry is to gain a seamless network operation to improve the energy efficiency of the wireless network. Applying AI in the planning process. In the planning process, AI is used to predict the traffic demand. In AI-driven traffic prediction, there are two types of traffic tendencies: short-term traffic tendency and long-term traffic tendency. Applying AI in network monitoring. Network monitoring and maintenance is the most complicated process. It is very difficult to analyze the requirement of customers because it dynamically changes, so maintain the network according to their request is a tough process. Applying AI in service monitoring. To monitor the quality of service and QoE for any network is the most important task. Using AI for this purpose will give an accurate result. Future research directions. The major research challenges are outlined in this chapter. A widespread effort is required from academia and industry in this area listed to contribute to green communication. Energy saving in telecommunication equipment using AI. Telecommunication systems and operators are having a large number of equipment and data centers. These data centers are made by many hardware like processing unit, input-output devices that consume a large amount of power for operation. Therefore, the communication system is facing a shortage of power and energy. Various power-saving techniques based on AI like deep learning and machine learning is using to fight with this serious situation. Ability to improve data interaction. An AI-based system organizes the available data in a very effective manner and converts this data into relevant information. More effective and efficient collaboration. The benefits of AI in a collaborative manner comprise sending information more effectively at a global level. For example, real-time language translation, fast feedback, and accurate scheduling. Secure and seamless services. AI-based applications motivate the intelligent security management system. Based on AI services such as big data, cloud computing, and IoTs are the technologies that provide secure data transmission. Conclusion for the information and communication technology (ICT) industry. The next-generation AI-based 5G communication network is considered as the key enabler and offers a diversity of features and services with various requirements. This chapter represents the mutual concern of the AI and next-generation wireless communication systems and technologies. The AI-based 5G wireless communication network will adopt a greater number of candidate recent technologies in the future. Therefore, to manage and monitor the next-generation wireless communication, inclusion of AI with communication is very important. In this chapter, advanced wireless networks like MIMO, M-MIMO, UDN, MM-Wave, and D2D communication for 5G network designing and the relationship between AI and green communication are discussed. Applications and future research directions of AI-based wireless communication are also highlighted in this work. The prediction is that AI-empowered 5G communication networks will make the acclaimed ICT enabler a reality. Acknowledgement. The authors would like to thank the Women Scientists Scheme under the Department of Science and Technology, Government of India for its financial support of this work under File No. SIWOSA, ET 154/2017. Chapter 18, Data and Systems. Knowledge representation and reasoning in AI-based solutions and IoT applications. Marcus Tanque, independent researcher, United States. Artificial intelligence, AI-based solutions, knowledge representation and reasoning, and the Internet of Things applications have transformed how researchers and practitioners view the analytical and computational capabilities. The disruptive evolution of these technologies has encouraged researchers and practitioners to develop integrated AI-based analytical solutions needed for solving pervasive issues affecting computational applications. The capabilities include AI, knowledge representation and reasoning, and Internet of Things. Such capabilities are designed to support AI-based solutions, knowledge representation and reasoning, and the Internet of Things (IoT) applications. These technology trends involve relevant computational areas, that is, intelligent devices, sensors, autonomous vehicles, robotics, virtual reality, augmented intelligence, and others. The study addresses and validates solutions on how researchers can solve issues that affect AI, knowledge representation and reasoning, and IoT applications. Artificial intelligence, machine learning, intelligent machine, artificial neural networks, cognitive science, deep learning, artificial general networks, knowledge representation, and reasoning, cognitive informatics, Internet of Things introduction. The chapter explores and addresses the intersection between knowledge representation and reasoning, KRR applications, artificial intelligence, AI, solutions, and the Internet of Things, IoT, objects, notably intelligent devices and sensors. This chapter focuses on smart homes and cities. It discusses the fundamental transformations that researchers have made in the fields of KRR, AI, machine learning, ML, deep learning, DL, and IoT, 1-2. Hybrid AI KRR capabilities interact with human-to-machine and device-to-system, 3. AI is an integrated, technology-based capability which incorporates human intelligence, HI, and smart objects, such as devices and sensors, 1. The triad forms a single or multiple computer systems capable of performing massive workload computer processing, 1. AI-based solutions are developed to support and solve various events, 3. The studied process involves human insights, ability to ensure the performance of smart objects, and determine when these sound devices and sensors can interact. AI has reshaped the global technology landscape through its incorporated analytical capabilities. 1. Background: in the last 2 decades, KRR, IoT, and AI-based capabilities have been used to support other technology domains. This technology evolution involves HI, smart devices, sensors, and reasoning systems that interact when deployed in a decentralized IoT networks. 2-4. This advance is due to continuous technological innovations involving AI, KRR, ML, DL, artificial neural networks, and IoT devices and sensors. KRR is a subclass of AI that focuses on data displaying and processing. 1. The research discusses other interdisciplinary areas, such as psychology and mathematics. 1-2. In 1955, John McCarthy coined the term AI as a science and engineering of making intelligent machines. 5. In the summer of 1956, McCarthy organized a technology workshop at Dartmouth College. At that conference, other AI research leaders, namely Alan Newell, Arthur Samuel, Herbert Simon, and Marvin Minsky, joined McCarthy. 6. As part of the conference proceedings, these experts presented a research project on AI topics. The researchers also received positive feedback from those in attendance. Those who attended the workshop at Dartmouth in 1956 were deemed to be one of the AI research leaders. 7-8. These researchers, along with a group of students, developed a computer program called Astonishing. In 1954, AI researchers conducted an array of tasks to satisfy past research work. Those projects led to successful technology breakthroughs, some of which today are called AI, KR, ANN, HI, ML, and DL. 5. In 1959, computers were able to play the checkers strategy game at a much accelerated pace than an average human. Checkers strategies consisted of information processing system-based games that researchers designed to solve issues involving the algebraic proving logical theorems. 5. Knowledge representation and reasoning. Knowledge representation, KR, is a method that involves formalism. 4. KR is a subclass of integrated AI functions. 4. It lies in the accepted concept and design theories for information visualization, logical thinking, and processing. 3. This concept includes semantic networks, SNNs, systems architecture, frames, rulers, and ontologies. Automated reasoning differs from inference engines, theorem provers, and classifiers. 4. AI is a domain that integrates technological areas, namely HI, computers, and intelligent machines. 3. 9. These domains range from AI intelligent systems to fused KRR capabilities required to process tasks through perceptive methods. 2. 4. AI dates to the era of the Greek philosopher Aristotle's earliest events. Aristotle's findings examine the relationship between philosophy and logic concepts and theories. 3. Aristotle describes reasoning as syllogism. 3. 9. He defines syllogism, a speculation that involves objects, ideas, factors, events, phenomena, or entities. A syllogism describes initial results in Aristotle's investigative methods. 3. Whereas the term reasoning has originated from the disciplines of computer science, sociology, and psychology. In contrast, logic is a process for gathering and blending methods. It operates at the heart of an assumption that man makes to ensure collaboration of two or more concepts and thoughts. 9. This concept illustrates different forms, such as providing or displaying data through analytical conclusions. 9-11, as summarized by McCarthy. 10. A program delivers a common sense if it automatically deduces for itself a sufficiently wide class of immediate effects of anything it is ordered, and what it already knows. For a program to be capable of taking something, it must first be capable of being stated it. Programs with common sense. 10. Knowledge engineering. Knowledge engineering, KE, plays an essential role in applied AI research sphere. Researchers argue that an idealistic way to address KRR, AI, KE, ML, and DL issues is by collecting and parsing data. This method ensures that researchers have the capacity they need to examine machine reasoning and how each of these systems can do specialized jobs. Thus, KE is a cognitive operation that represents scientific and societal features. Such method plays a critical role in designing and supporting knowledge-based systems. Expert system. Expert system, ES, is an application that clinicians use to carry on medical diagnoses. 12. The first ES did not embrace a standardized functional process. Hence, the system lacked the capability researchers needed to extend their investigative scope, which subsequently contributed to the development of inference engines and software applications. 12. The original ES consisted of the following software processes, conventional and development methods, and the need for designing unique programs for tuning or streamlining the requirements for building ES. Whereas knowledge acquisition, KA, gives companies such as Anderson Consulting the ability to secure research opportunities. KA ensures that the redesigning processes use different versions of prototypes. 12. Knowledge inference, forward and backward chaining, and KL1 languages. Knowledge inference, forward chaining, FC, and backward chaining, BC, or backward reasoning, BR, and KL1 languages are applications or engines that are being employed today. These applications processes are deployed along with ES prototypes. 12. ES is a hardware that stores large volumes of datasets. The stored data contain large volumes of data or datasets about the world. On the contrary, focuses on dual methods of reasoning prototypes. 12. Researchers argue that this process occurs when there is a logical description of the interface engine. The ES implementation process is extremely complicated. The logical process moves the commercial enterprise and production-based rule system prototypes. 12. BCBR is a process that relies on artificial intelligence applications, IAS, automated theorem evidence ES, and proof assistance. BC and FC are concepts integrated in AI, game theories, and other ES prototypes. 12. In KE, domain ontology, DO, and domain-specific ontology, DSO, describe many things, such as objects that exist around the world. Humans view ontology as a process, which involves poker domain prototypes. 12. This concept describes a method for modeling computer hardware, notably punched and video cards imports, and others. In the DO, ontology meanings are interpreted through domain perceptions prototypes. 12. In 1977, Ronald J. Brackman discussed the term KL1 in his doctoral research. KL1 is an integrated NR system. 13. Preceding Brackman's research work, other scholars conducted more studies focusing on representation. The research was independent of other studies that incorporated similar domains. KL1 permeates the representation of the indistinctness in SNNs. Its process describes technical data, logically, called a structured inheritance network. 14-15. This method aims to new technologies, namely epistemological level, EL. EL focuses on dealing with complex concepts, such as attributes, instantiations, descriptions, uses, and inheritances. 14-16. Brackman, 17, states that, in early investigative studies, each of these concepts was illustrated as representation systems. 18. These systems range from traditional and technological SNNs and form networks, FNNs. The progress and fine-tuning methods have improved over the years. These schemes are used in scientific research areas to implement new knowledge-based concepts and basic research methods for the AI society. 15. KL1 kernel points out that AI researchers rely on to formulate structured complex descriptions. 15. This knowledge-based method is applied to identify and defines the relationship between network theories. 13. SNNs or FNNs are networks that describe systems, which can be deployed to a KR environment. These systems focus on direct and undirected graphs equipped by the vertices. 13. In this context, vertices symbolize concepts and edges. Vertices describe relationships between concepts. 13. SNNs are identified as semantic triples. The networks are used to support an array of applications, such as NLP. 13. Technological Singularity and Recursive Self-Improvement. In 1959, Alan Newell and Herbert A. Simon developed KR. KR is designed to resolve complex issues affecting technology singularity and recursive self-improvement. 4. Newell and Simon developed a method to integrate, plan, and analyze data structures. 3. These strategies stem from outlining conceptual plans to supporting predicted outcomes. AI solutions are deployed to support general search algorithms. 19. These procedures include A*, frequently known as a star. The A* computer algorithm was produced to support AI solutions and issues involving GPS systems. The failure of these scientific research efforts resulted in a cognitive change. 319. Explains an adapted logical relationship between the triangle of cognitive science fields. 319. The picture in a theoretical explanation for cognitive skill fields and variables. Cognitive science studies. Artificial intelligence (AI) provides intelligent machines with the ability to translate external data. 6. AI collects and examines datasets to help identify, predict, and probe the origins, applicability, or qualities of data needed for processing. In AI, the process to visualize data gives analysts and scientists the ability to discover and display dataset patterns. 1.6. Decision-makers rely on the collected, analyzed, and processed data to draw informed decisions about specific goals and tasks. 6. The complexity and lack of scalability affecting neural networks are different from that of the traditional systems. 1.3. In AI, regression reasoning can be insignificant, irrespective of the relationship that these variables display in a limited heuristic reason. 3.10.11. Kaplan and Heinlein. 6. Cite AI researchers argue that traditional computer systems are not immune to comparable functional behavior. Despite these integrated intelligent functions, AI shows pseudo-intelligent reasoning. It incorporates strong and weak behaviors within the environment. These computers often display a substantial degree of parallelism. 3. Weak AI consists of information processing system-based applications that have limited interaction with other intelligent objects. 5.6. This method stems from applied knowledge and exceptional characteristics, that is, autonomous systems and heuristic ability search algorithms. 10.11. Despite the progress that scientists and researchers made, AI-based organizations view performance limitations as a challenge to AI technology. These technical constraints include strong and weak AI capabilities. Such restrictions are attributable to systems with autonomous interaction. 3. Artificial intelligence for information technology operations. Artificial intelligence for IT operations, AIOPS (AIOps), was previously known as Algorithmic IT Operations Analytics. AIOps is a solution that provides agile and cost reduction for public and private sector. AIOps is an umbrella term that was coined for advanced technological domains, ML, big data analytics, and AI. Researchers developed AIOps to provide technical support for the identification, automation, and resolution of various issues affecting the IT field. In the recent decade, business, scientific, and research communities have used AIOps to monitor IT solutions while acquiring clear visibility into dependencies beyond IT systems. Despite this adaptive terminology, researchers define AIOps a platform which syndicates big data and AI functionalities. AIOps focuses on IT operational structure. For example, AIOps processes tasks, executes, deploys and provides continuous backup to functional areas in the enterprise. Commercial enterprise and technological functions can be deployed as a toolkit. AIOps capabilities support performance monitoring, event requirements, and business data analytics solutions. IT service management and automation offer customers hybrid technical solutions to ensure that middle management and senior executives have the capability they need to make informed decisions. AIOps capabilities are vital to an organization's mission success and agile IT resource distribution. AIOps delivers integrated technical functions, such as propelling an organization's business capability, while providing infrastructure, continuous monitoring to support end-to-end IT solutions. Engineering science measures, automates, and monitors business practices to boost productivity and increase efficiency or streamline operational delivery timeframe. AIOps platforms are deployed as technical solutions to support enterprise integration of IT solutions. Such solutions involve monitoring, automating, and providing maintainable business functional posture needed to sustain the holistic enterprise functioning. Managers and executives rely on these cognitive operations to make informed decisions. Organizations should invest in AIOps capabilities. These IT solutions are vital to organizations' digital business transformation and sustainability. The integration of AI into IT operations ensures that businesses have the seamless capability needed to perform at a faster rate and supply that the layer of productivity. AI, KRR, and IoT functions. In 1956, John McCarthy coined the term AI at a conference organized by Dartmouth as part of his scientific exhibition. CS involves the following technical areas: 19, psychology, linguistics, anthropology, AI, neuroscience, and philosophy. In the same year, McCarthy devoted more time to research on parallel topics: NLP, image identification, sorting, and ML. McCarthy's research yielded significant AI results, from most of which many industries have used for many years. 319. Today, research and development and academic institutions are taking advantage of these AI-based results to grow operations management functions. 3. Technology assets and technological resources. 10. Implementing AI and KRR capabilities gives clients the tools they need to operate effectively and efficiently in the digital era. 2-4. Despite this progress, other industries have employed similar AI/KRR processes to support their daily operations. These industries describe AI and KRR as different things. 3. Many researchers state that AI and KRR can be embedded with ML and DL to provide a hybrid functionality. 3. AI is a subclass of computer science that focuses on the study of human behavior. Researchers argue that AI does not focus on human behavior only. Instead, it encompasses the interaction between humans and computer systems. The process includes complex activities that comprise awareness, perceptual experience, reasoning, mimicking, and the environment. 10. These computer systems consist of swarm intelligence, SI, networks, standard algorithms, intelligent robotic systems, and neural systems. 1-2. There is a sheer functional characteristic between traditional computer systems and IS. The variances between the core and established systems or the AI-based applications include, but are not limited to, 2-4 sophisticated and functional features involving AI-based applications, a complicated step-by-step algorithmic procedure that computer systems should play along to execute to perform functions effectively, and the time AI computer systems need to model and process data in non-typical functional behavior. In the 1950s, cognitive revolution was an experimental intellectual term. This term was named as cognitive science, CS. CS involves transdisciplinary or systematic areas that emphasize the underlying research on HI and operations. These methods include the functions executed in the CS and cognitive functions of human awareness. In the last decade, cognitive scientists developed the use of logical thinking to analyze the behavior and intelligence of the human mind. 19. Reasoning defines the computer logic needed for automating and sorting distorted scientific issues. It further describes how humans utilize the application of instructions amid a group of objects and subclasses of relationships. 1-3. Researchers are studying neural systems, theatrical performance, and how these operations can be enhanced to process information in real time. This process includes language, belief, attention, thought, memory, and emotion. Artificial intelligence applications and tools IS solutions are designed to solve complex problems. These products provide the capacity required to hold up the decision-making process within an organization. 3. IS relies on integrated applications, that is, chatters and others. The results are projected to mimic HI by providing seamless, timelessness, consistency, and cost-effectiveness unified technical and business approach. 3. IaaS are deployed to solve complex issues that may affect an organization's daily operation. Some of these problems range from system agility and holistic IT solutions that decision-makers need to make informed decisions. 3. These processes provide decision-makers with the tools they need to make an informed decision, using qualitative and quantitative data processing methods. Many researchers indicate that AI is a technology that its analytical methods have not fully matured. 3. IaaS continue to support different businesses while collecting, assessing, processing, monitoring, and furnishing decision-makers with automated toolkit needed to solve complex issues. 3. AI analytical processes consists of algorithms, mathematical optimization, and advanced computational reasoning. These presented solutions are developed to solve AI complex issues, such as broad-based scientific solutions integration. The following processes are built into the artificial intelligence tool, AIT, operationalization, 2 for logical thinking, premises to conclusions, inference, rule planning, means ends analysis, robotics, local searches in configuration space, learning and optimization. 8 include various research and development areas. AIT was developed to solve complex issues involving AI. 2 4. In AI, logic is a cognitive operation that supports KRR and problem-solving processes. 3. The advocated methods can be used interactively to support IT operations, some of which involves algorithms, planning, and logic programming. Each of these results are provided as integrated capabilities to sustain the scholarship process. 3. Machine learning and deep learning (ML) is part of the AI. There is a symbiotic relationship between AI, ML, and DL. 20. AI provides learning process categories, for instance, unsupervised, supervised, and reinforcement. 21. Unsupervised and supervised learning processes focus on the classification and mathematical regression theories. ML is implemented when machine classifications of things are allocated into various groupings to achieve a unique business objective. This process applies to regression, which is a practical solution a single machine can generate as a function. This solution produces inputs and outputs. 21-22. How these inputs and outputs generate roles is key to delivering ML operational functions. In this context, the agent is rewarded for giving first-rate answers. The process runs agents analyzed for incorrect responses. 22-23. In the ML, agents depend on rewards and punishments to find practical strategies. Some of these concepts are designed to ensure that intelligent machines perform within assigned AI boundaries or settings. 23. For that reason, unsupervised, supervised, and reinforcement learning strategies that can be broken down within the decision theory and through the operation of judicial decisions, that is, utility and others. Robotic process automation. Robotic process automation, RPA, is software that involves AI and ML solutions. RPA processes volumes of metadata and datasets. The term robotic process automation dates back to the early or mid-2000s despite its existence that goes as far as many years ago. The term spans a trio of technologies, notably screen scraping, workflow, the automated arrangement, as well as AI-based solutions. 23. Screen scraping involves machine processing and data display screen collection. Its capabilities range from traditional applications needed for data displaying through the user interface methods. The automated workflow software streamlines the process that takes for data to be sent to multiple system interfaces manually. This progress gives mechanical systems a continuous capability needed to increase the production timeframe, like efficacy and accurateness. In IoT, This process is agile and interactive, allowing for computer systems to deliver requested or assigned services without experiencing any single point of failure. 22. The concept involves tasks that, in the past, humans used to achieve them. In the database, AI and ML projects involve queries, computer or computerized processing, electronic record keeping, and other types of business transactions. 23. RPA is not an enterprise IT infrastructure enablement application. RPA can be offered as a software as a service, SaaS, enterprise solution to facilitate smooth deployment of technical capabilities. The technology cycle will take place without impacting IT infrastructure downtime. 22. In ML, the mathematical analysis is a branch of theoretical computer science. 22-23. The field is a computational learning theory, offering robots the capabilities they need to acquire new skills and to adapt to other environments. This unified capability supports autonomous self-exploration and social interaction involving human educationalists. Steering mechanisms, like active learning, development, and other synergic aspects can be arbitrary and repeated throughout the general learning process. 24-26. DL is a computer science discipline that includes other technology areas, such as deep network learning, and cognitive computing. These three key areas are built upon computer science concepts. Vendors and researchers have used the term cognitive computing to exemplify a significant association between these technological areas, DL, deep network learning, and ANS, 3. This term is generally applied and converged to support the enterprise in part. Researchers examine DL and related technologies as rapidly evolving phenomena. AI objects can process data with limited human involvement. 22-23. Planning, scheduling, and learning. Planning, programming, and learning are processes that provide intelligent agents, AIs, with the capability to determine and achieve realistic objectives. In classical planning problems, the agents can exceed that within an AI only one organization should be deployed and running at the time. Such concept, yet, allows brokers to be precise about the consequences surrounding similar activities. 23. The below list explains an existing relationship between the hierarchical AI-controlled organization. Such an association includes the relationship between actuators, sensors, controlled systems, operations, and environs. Top-level Node O specific goals and projects O sense data and results O Node 1. Actuators' actions can be embedded into the controlled system, process, or surrounding sensors' sensations from the controlled system, method, or environment into sensors O Node 2. Actuators' sensors' actions from sensors to actuators into the controlled system, method, or surrounding sensations from the controlled system, method, or environment into sensors to actuators if a single agent or multiple brokers are not acting alone within AI. The desired process assumes that the assigned agent can reason through a layer of ambiguity. This process ensures for agents that are incapable of inept or understanding environments to make proper estimations, or become accustomed to a specific or assigned designated environment. 23. Internet of Things. In 1999, Kevin Ashton coined the term Internet of Things after conducting several types of research at the Massachusetts Institute of Technology, MIT, Auto ID Center. Ashton preferred to address it, Internet for Things. 27-28. Ashton embarked on a new research project involving the radio frequency identification, RFID. Through such complementary research findings, Ashton was able to incorporate RFID technology into IoT-based applications. This advance allowed objects to interact and manage data or other things through a distributed or an interconnected physical network. 27-29. IoT is a dynamic network of distributed and decentralized or distributed physical objects. IoT consists of smart devices and intelligent systems. 30. These smart objects can be embedded as sensory systems, RFIDs, actuators, driverless vehicles, smart buildings, and closed-circuit television. 27. The objects range from smartphones, tablets, smartwatches, home appliances, and consumer applications, explicitly creative industries, home automation, and wearable devices. 31-32. These technological solutions can be equipped with network connectivity beyond standards. This method allows devices and organizations to collect, examine, exchange, and store data in real time. 31. More consumers have smart devices connected to interconnected distributed networks. 32. These objects can be interlinked via the Internet with the ability to send or receive data. These objects' embedded functions are designed for remote monitoring and supervisory. 27. According to Wigmore 32, the number of IoT objects in late years has developed significantly. This disruptive technology surge is due to a rapid increase in AI, ML, DL, commodity sensors, and others. 32. The demand for innovative methods to power the IoT devices and organizations is paramount. 33. In 1982, a group of researchers discussed IoT technology at Carnegie Mellon University. The discussion was about a technology concept on a Coke vending machine. It involved proof of concept entitled Internet Connected Appliance. In the same year, McCarthy dedicated time to research on parallel topics, notably NLP, image identification, categorization, and ML. His research yielded significant AI results, which comprised AI analytical processes, that is, search algorithms, mathematical optimization, and advanced computational reasoning. These domains are deployed to solve AI complex issues through a wide-ranging scientific solutions integration. The proposed methods can interactively be applied to support processes, for example, algorithms, planning, and inductive logic programming. These methods allow for a unified and principal learning process among smart objects. 3. AI objects can process data in real time and interact with limited human involvement. 22-26. If a single agent is, or multiple agents are, not acting alone within an AI, the desired process assumes that the assigned agent can reason through a degree of ambiguity. According to Wigmore 32, IoT objects in late years have developed significantly. In essence, such disruptive technology scale is due to a rapid increase in AI, ML, DL, commodity sensors, and others. 32. The demand for innovative design methods to power the IoT devices and organizations is paramount. 33. In 1982, a group of researchers discussed a revolutionized IoT technology at Carnegie Mellon University. This treatise was part of a technology concept on a Coke vending machine. It involved proof of a concept entitled Internet Connected Appliance. Internet of Healthcare Things. The emerging of mobile technologies in the digital era has increased considerably. This rise is due to the constant demand for patient care, data provisioning, and the modernization of the electronic health record (EHR) system. Tech companies and governments are on the verge of modernizing and deploying their capabilities to meet patients' needs better. Most of these revolutionary transformations in public, private, and government sectors are due to the increase of patient data, for example, private EHRs. 34. The Internet of Healthcare Things, IoT, is a concept that involves mobile technologies, ranging from intelligent systems, sensors, and wearable devices. This method includes smartwatches that can be deployed in the distributed or decentralized IoT networks in support of the patient EHR system. As a result of the disruptive and ubiquitous challenges that the governments and industry have dealt with in the past decade, data provisioning, visualization, parsing, and allocation, and the need to modernize legacy healthcare infrastructure are paramount. 34. IoT involves intelligent devices, mobile technologies, and smart machines. Vendors are still grappling with developing a new analytic baseline that supports the EHR modernization and data provisioning via integrated cloud solutions. In the IoT environment, intelligent devices and sensors are deployed to collect and process data with less time than the traditional healthcare systems. The need for a flexible and integrated healthcare system will ensure that providers and patients have a continuous interaction and the ability to share information in real time. This interactive capability can only be possible if a robust healthcare infrastructure is built to support such a patient's need. Through biometric technology, patients and providers would be able to share private data and ensure for its protection. 34. Real-time health systems. Real-time health systems, RTHS, are convergence and integration, data collection, and intelligent sensor-based systems that can be deployed to collect patient information via IoT platforms. These devices comprise mobile technologies such as RTHS. Mobile devices collect, analyze, and process data between RHTS and IoT devices. Data sharing is processed via the RTHS integrated portal. In the clinical data ecosystem, EHR does not only address patient-based situational awareness. 34. It collects a patient's health information besides the care that each patient can receive at any medical facility, like hospitals or clinics. This application captures patient's critical data. RTHS is responsible for gathering, analyzing, and processing the patient information and make it available to the assigned clinicians, who are accountable for the patient's continued care. 34. RHTS collects IoT patient information, parses and provides actionable clinically based results. The data offer relevant indicators and trends concerning the current patient's health status as well as continuing treatment. 34. Within an integrated EHR/RTHS environment, patients and providers can exchange data securely and in real time. Researchers note that this revolutionized the healthcare capability industry, predicting for many years. 34. Vendors argue that more work needs to be done to ensure that the EHR system continues to meet patients' and health providers' needs. With the support of RTHS, health providers are now able to collect, process, and analyze patients' confidential data faster. This process encompasses identifying clinically relevant datasets, indicators, and forecasts that providers use to predict future illnesses. Establishing an integrated and friendly solution that providers need to monitor data and alert the patient of potential or catastrophic diseases, some of which might lead to death. These health IT solutions include mobile devices that are paramount capabilities of a patient's continued healthcare. 34. With the new and integrated health IT solutions will be able to provide the patient with real-time notifications of probable illnesses and ensure that such diseases are treated immediately before reaching an irretrievable stage. 34. Natural language understanding and interpretation. Natural language understanding, NLU, is a subclass of NLP. In AI, NLI is a technology area that focuses on the study of machine reading comprehension. 35. It addresses AI complex issues. 36. In 1964, Daniel Bobrow from Massachusetts Institute of Technology made the first computer try to address NLU. 36. Aside from Bob Rowe's ambitious attempt presented in the dissertation entitled Natural Language Input focused on the computer problem-solving system, nearly 8 years later, a proven AI researcher, John McCarthy, invented the term AI. NLU focuses on global marketable relevance, straddling IS, to systematized analysis and reasoning. 36. The NLI method involves the following AI areas. 36. Machine translation, question answering, news gathering, text categorization, voice activation, function archiving, large-scale content analysis. These significant areas incorporate text post-processing, which is central to NLP algorithms, stage processing, along with some parts of speech identification using context from other recognizable devices such as automatic speech recognition and sight recognition. 36. NLU is a term that can broadly be working in AI, robotics, and other complex software engineering fields. Researchers suggest that this applied method can be used in computational applications involving small, medium, to large-scale tasks that are assigned to robotic systems. 36. It can support diverse computer applications, for instance, text classification needed for email automatic analysis, and others. NLU focuses on promoting and sharing pieces of standard algorithms elements, explicitly language lexicon, parser, and grammatical rules, needed to divide or to structure sentences as well as core illustration. Semantic theories must complement IS. These theories are developed as interpretative capabilities to translate applications in the language understanding system. In contrast, semantic methods consist of 36, naive semantics, stochastic semantic analysis, pragmatics, and semantic parsers. This concept spans technologically advanced applications aimed at integrating logical inferences into the framework. In NLU, there are two types of logic, that is, predicate logic and logical deduction. These logics, when simulated or applied to NLU, aid in reaching logical conclusions. 36. Classic artificial intelligence method. Many researchers describe the classic artificial intelligence method, CAIM, as an early version of AI. Researchers invented CAIM to process and support extensive computer programs and network applications. It focuses on translation of complex mathematics, algorithms, and computer problems, preventing human brains from performing any activities. The need for user-friendly computer applications to interpret text messages and related software features is paramount to CAIM's functions. These applications traverse the human's ability to recognize AI objects in an image. Researchers argue that more research findings will improve AI solutions. At present, there are millions to billions of IoT objects on the planet Earth. These intelligent devices and systems are generally deployed to several areas to perform a straightforward or complex activity or mission. IoT devices are ubiquitous objects that can be found almost everywhere around the world. Researchers predict that in the coming years, there will be trillions of IoT objects around the world. These objects will be deployed to support various activities and missions. 319. The need for user-friendly computer applications to interpret text messages and related software features is paramount to CAIM's functions. These applications intersect the human's ability to recognize AI objects in an image. Researchers argue that more investigative findings will improve AI solutions. 319. As many researchers would antedate, natural intelligence, NI, is not a subset of AI. Instead, it incorporates systems of control, which are not artifacts. NI involves the functioning of animals and human brains. 37. AI objects comprise neuroscience. Researchers believe that NI continues to play an integral role in the medical field. 37. With the advent of AI, KRR, and OCR, many researchers suggest that physicalism and functionalism, can be the two breakthrough assumption that often gives an insight into how the human mind functionalities. Identicality in human reasoning is documented as a reductive method that associates one's intellectual faculties with other human phenomena, like neuronal activities. The mind can trigger responsiveness and intentionality toward an environment. Such action leads to a perceived responsiveness and actable stimuli within the brain. This involuntary activity in the human mind prompts the human brain to begin thinking, while generating perceptive feelings toward others or an environment. 38. Learning using privileged information. Learning using privileged information, LUPI, has been used in academia, industry, and other business sectors. LUPI is a process that transfers knowledge such as privileged information. In the new learning developmental paradigm, LUPI constitutes a part of the training phase that includes multidimensional methods needed for delivering tangible results. Vapnik and Vashist adopted and popularized LUPI as a transformational concept. In academia and industry, LUPI is used to compare data, provide a consistent level of reasoning. This approach involves logic, emotion, or metaphorical reasoning. LUPI privileged information may involve confidential communication, non-disclosure agreement, and need to know. Privileged data is a process that handles confidential data, such as patient records. How data are handled, processed, and shared is essential to the provider and the patient. In ML, LUPI denotes a new paradigm that balances the digital era of information, technology, innovation, and processing digitized resources over the enterprise. Such concepts may be conditions for consistency and how machines may learn from their environments. LUPI focuses on practical algorithms, for example, support vector machines. In each environment, machines are programmed to execute diverse functions. These roles include processing or ruling potential algorithmic outliers. LUPI is embedded in technology and science. This method focuses on human and classical ML systems. Picture Archiving and Communication System. Picture Archiving and Communication Systems, PACS, are used in the healthcare industry. PACS is a medical imaging solution that ensures clinicians have the permission to store the patient's confidential and non-confidential information. The solution gives healthcare providers access to cost-effective storage capabilities. This repository retrieves patient's data, such as archived dental and medical records. Using the AI and ML technological capabilities, medical providers are now able to view images that are daily received and processed from multiple sources of intelligent devices and sensors. In the PACS healthcare ecosystem, electronic images and other data can be uploaded, processed, and parsed digitally. This healthcare e-capability focuses on streamlining the processing time that providers often take to send and share a patient's information to selected entities within the medical community. This technology has given medical practitioners and providers the capability they need to conveniently access, retrieve, parse, view, and processing patient's data in real time or with a limited human error. Due to this critical process, today, practitioners can conduct computed tomography, magnetic resonance imaging via a dedicated, distributed, or secure network system. The process ensures that a patient's data can be transmitted and viewed through a secure portal. This capability protects and secures patients' confidential medical records. The technology streamlines and minimizes physical and time barrier-based accessibility to confidential patient data, which unauthorized users may obtain. The data are stored on the provider's medical database systems. With the disruptive and ubiquitous IoT intelligent devices and sensors, providers can process patient's images or other confidential data with minimum, without disruption to the provisioning system. The PACS consists of 4 distinctive domains. Each of these domains can provide remote access, electronic image integration platform, and radiology workflow management. PACS has a robust capability to process data between local and wide area network distributed nodes. These capabilities can be deployed via a virtual private network and a secure socket layer. It supports interactive applications like ActiveX, JavaScript, and Java Applet. Infrastructure-based mobile networks. The industry continues to research and develop proven infrastructure-based mobile capabilities, like ad hoc networks, to fulfill customers' urgent and long-term needs. These decentralized capabilities come in many flavors, such as those equipped with intelligent sensors and devices that can provide quick and responsive results. The network infrastructure consists of a hardware and software solution that is implemented to support an IT environment. 39. These IT resources are used to provide seamless connectivity, communication, operations, and management solutions for small and large networks. Through these capabilities, users can share services and data through decentralized, distributed, unified, and interactive IT networks. Wireless and mobile ad hoc networks are vital to day-to-day customer IT requirements. In the IoT, ad hoc systems are deployed to support other hardware and software solutions. 39. IoT consumer applications. IoT consumer applications continue to play a crucial role in the integration of smart objects needed to support interact with MI, ML, DL, and KRR applications. 27. IoT spans a total of 6 consumer applications. These applications comprise the following IoT consumer applications. 2739. Home security and smart domestic. This type of IoT consumer application includes domestic safety, DS. DS is a critical area that has promoted the IoT services. Despite this progress, researchers concluded that in IoT, most devices and systems continue to experience network and security vulnerabilities. Such breaches are due to a series of weaknesses and threats affecting IT assets. Vendors have been working tirelessly to develop new software applications to avert or minimize some of the weaknesses and threats against the IoT devices and systems. Home security often ranges from a method that is designed to provide home appliances the level of protection needed to protect them from unauthorized users, for example, hackers and intruders. These devices are acquired and deployed in homes, business offices, and related facilities. Most of these objects can be attained in the market at an equitable economical price. Private healthcare, healthcare carriers, and healthcare players. In healthcare, IoT devices and systems have been deployed to provide governments and enterprises with proven capabilities needed to support mission-critical solutions. These solutions can be deployed in smart homes and smart cities. These capabilities are designed to provide the ecosystem with a blend of continuous monitoring capabilities needed to protect data and patient records. Similar IoT devices are deployed or used as a wearable device that clinicians can use to diagnose patients. These wearable devices are ubiquitous in the sports industry. Athletes use these types of tools to monitor activities on the field, for instance, following heart rates, steps, and among other things. Such devices have the capabilities of monitoring, collecting, uploading, and storing data to a remote repository for future processing. Wearable technology, in this context, are used in either individual or multiple persons' activities. These devices have been used in sports or in healthcare, but also for one's daily use. Some people use wearable devices instead of watches or other types of tools designed to serve a particular individual's purpose. In heavy industries, these smart objects are used as smartwatches and health monitoring devices. vendors continue to develop new methods that can better meet the consumer's day-to-day requirements. Asset tracking: valuable assets, wearable devices that can be employed as technology assets, which serve the consumer's needs. The Global Positioning System is a perfect example of intelligent machines that monitor or track an individual's requirements. IoT consumer applications have evolved over the years. This rapid evolution in IoT is due to the advent of advanced applications that vendors have built in recent years. Workplace: having IoT devices and objects deployed in the workplace can improve the level of work while providing the level of security that decision-makers and employees might need. Today, most of these devices and objects can track, store, collect, and disseminate actionable data to relevant sources within the workplace by providing continuous monitoring within a physical security perimeter for the ability to function as sensors. Most sensors are designed to adjust the room temperature in residential and commercial buildings. IoT devices play an essential role in everyone's individual life and in the workplace. These devices and objects can perform activities beyond the human imagination. Some of the devices and objects can be found in luxurious resorts where people often plan annual vacations. There are millions to billions of IoT objects on the planet Earth. These devices and objects are generally deployed to several areas to perform complex activity or mission. IoT devices are identified as ubiquitous objects and can be deployed almost anywhere around the world. Researchers predict that in the coming that is the heart of artificial intelligence to solve pervasive Internet of Things issues. If it helped, a quick subscribe keeps more summaries coming. So how do data and communication connect? That is exactly where we started. Go back to the top and watch it click into place.